Okay, we are now ready to start a new section of the class, a new major section of the class on equilibrium statistical mechanics. As I've said many times in the class so far, statistical mechanics gives us the laws of thermodynamics, and especially a lot of the properties of thermodynamic systems, especially equations of state for thermodynamic systems, by calculating those quantities directly from the properties of the atoms and molecules themselves. So StatMech gives us a connection between the structure and properties of individual molecules and collections of molecules and the results that we need in order to make meaningful thermodynamic calculations. So that's one really big and good thing. But it does another thing also. Thermodynamics is really only good for large systems, systems that have maybe 1,000 atoms and molecules at least. Below that, for systems smaller than that, thermodynamics starts to break down, starts to fail in various ways. It still works in some ways, but it starts to break down, whereas statistical mechanics continues to work no matter how small the system is, even for a single spin. So just one feature of one nucleus of one atom behaves and can be understood according to statistical mechanics. Probabilities can be calculated using statistical mechanics. So we're going to talk about the main rules for statistical mechanics in just a minute. But before we do that, I thought it would be useful to give a little bit of background for where the main results of statistical mechanics comes from. And so I'm going to talk just for a minute and just a little bit about this topic I've called Hamiltonian mechanics here, and this concept of phase space, which is a little bit beyond the typical thing you get in a class at this level. But I think it's useful in order to get a little bit better idea where the things we're going to talk about in a minute came from. So let's suppose I have a system like this, a collection of atoms and molecules. Then from a classical point of view, the state of such a system, the classical state of such a system, is given by the position of each atom and the momentum of each atom. So if I've got n atoms, then giving the 3 coordinates that I need for the position of any one atom and the 3 more coordinates that I need for the momentum associated with that atom, a total of 6 n coordinates altogether, that corresponds to 1 microstate for a classical system. And that state exists in a 6n dimensional space, hard to visualize, pretty much impossible to visualize, in fact, but we can still think about it and talk about it. And that space is called phase space. If you see that in books in the future, you will now know at least a little bit where that term comes from. The atoms and molecules are governed classically by equations of motion, which are Hamilton's equations of motion. And so when we're talking about mechanics, that's what we mean. We mean either classical mechanics or quantum mechanics. And if you were to solve these equations of motion, you would get the position of each atom as a function of time and the momentum of each atom as a function of time. In other words, you'd get the state of the system as a function of time. And then the question is, what could we learn from that? Well, that would give you all the positions of each and every atom and all the momenta of each and every atom as a function of time. There are very few cases where you really want that level of detail. There's almost no cases where you want to know the position of every atom and the momentum of every atom as a function of time. And the business of statistical mechanics is to take these kinds of facts and turn them into useful statistics that we can use to do calculations without having to actually solve these equations of motion. But if you were to solve those equations of motion, then in very simple cases, let's suppose you have just two atoms, for example, and let's suppose those two atoms are connected by a spring. A bond behaves like a spring, so this is a diatomic molecule, for example. And then you solve the equations of motion of the sort that I just talked about up here, and we won't talk about them in any detail, but they exist. And then look at how that motion looks in phase space. Then what you'll find for a harmonic oscillator like this, you'll find very simple motion. It's called non-ergodic motion. Non-ergodic just means we can make sense of it. It's a nice simple loop. The momentum and the positions are varying in a nice simple orbit, if you like, in phase space. And that's the kind of motion that you get when the sample is simple, when the system is simple. If the system isn't simple, then you get something that looks more like this. And so this is the more normal case, and this is ergodic motion. When you have something that's got a bunch of atoms and molecules, ergodic motion can happen even for very simple systems. And so even if you have a relatively small number of atoms and molecules, like the picture I've drawn here, then very likely, it's almost guaranteed, if you were to look at how that system is moving in phase space, what its path in phase space looks like, it would look something like this. It's a mess that you can't make any sense of. And furthermore, even if you could somehow find that path, you could solve those equations of motion at every instant of time and find that path, it wouldn't tell you what you mostly want to know. You mostly want to know statistical things or thermodynamic things. You mostly don't want to know this level of detail. So, the good thing about ergodic motion is, the bad thing about it is that it's complicated. The good thing about it is that if you let the motion go on long enough, then the ergodic hypothesis starts to become ergodic hypothesis, starts to become relevant. What the ergodic hypothesis says is that if I look at a small zone in phase space and I ask what's the probability of finding the system somewhere in that zone, then that probability is just proportional to the size of the zone. In other words, the probability of finding any one state in any one point in space is uniformly distributed. Just like in the picture that I've drawn here, you look anywhere in phase space and you find the same number, the same density, if you like, of curves filling up that phase space. And that means that if we don't worry about time, if we don't worry about the fact that things are changing or moving with time, we're going to find a state here, a state there, a state there, and they all will have equal probability no matter where we go. That's called the ergodic hypothesis. Here it is written out. It says, for a system of sufficient complexity, all microstates of equal energy, and the equal energy part is important, I haven't stressed that yet, but if you're solving the equations of motion, the classical equations of motion, then energy is conserved. So this is all of these are states of equal energy. So if you're looking at states of equal energy, then they also have equal probability on a long enough time scale. If you wait long enough, the system evolves and evolves and evolves, and its paths or its trajectory, if you like, fills up all of phase space, and that means that the probability of finding any one point in phase space is equal to all other points. Also, it means that if I want to find the time average of something in phase space, so if I observe something going on and I collect a whole bunch of data over time and then I take a time average, that's the same thing as averaging over all the possible microstates. in phase space. Even if I don't do a time average, all I have to do is average over all the possible microstates, and I'll get the same answer according to the ergodic hypothesis. Is the ergodic hypothesis, it's called a hypothesis after all, it's not the ergodic law. Is it good? The answer is that for very simple systems, it's not good. But it is good. You know, a whole bunch of really careful and rigorous theoretical work has been done to try to prove that the ergodic hypothesis is good, or to find conditions when they can guarantee that it's good. And so far as I'm aware, well, some progress has been made, but no really definitive answer has been possible so far. All we really know is that it's good for complicated or complex enough systems. And where that bar really is, nobody really knows. But if you've got 1,000 molecules, then it's certainly good. If you've got 100 molecules, it's almost certainly good. If you've got 10 molecules, it's probably still good. It probably doesn't stop being good until you're down to, I don't know, 3 or 4 molecules. Then maybe it's not good anymore. So we're going to use the ergodic hypothesis. You can see that it gives a probability measure, and we're going to use that to develop everything else in all of StatMech. The ergodic hypothesis is really the basis for all of StatMech going forward. All right, so given that, let's consider the probability for an isolated system. An isolated system is good because energy is conserved. Which means that all the microstates that can occur inside this isolated system all automatically have the same energy. No matter what I do, as long as I don't intervene from outside, all the motions that go on inside this isolated system all have the same energy. The system is isolated from the surroundings, the energy is conserved, and energy can't change if nothing comes in from the outside. And that means we're going to be able to apply the ergodic hypothesis right away. Let's suppose that for a system like this, we don't try to solve the equations of motion. We forget about the equations of motion from now on. We just count how many microstates the system has. So if I arrange the atoms the way they're shown here, atoms and molecules the way they're shown here, or if I change them, if I make this molecule wiggle a little bit, if I move this one a little bit, every way in which I can wiggle or change the velocity of atoms and molecules, as long as I don't change the total energy, or change the total number of molecules, or change the volume of my system, as long as I keep the outside constraints unchanged, then all those states count. They all have the same energy. They all count. I count them all up, and I call that number W. That's the number of possible microstates that are accessible to my system. According to the ergodic hypothesis, every single one of those microstates has the same probability. And if that's true, then the probability of any one microstate is the same as any other microstate, and they all have probability equal to just 1 over W, where again, W is the number of microstates accessible to the system. That's our basic rule. It's really simple. You couldn't really hardly ask for anything simpler than that. This W depends on what the energy is and what the volume is and how many molecules you have. If you change the system and then re-enclose it in its isolating walls and then recount what W is, you'll find a different number. But if you don't do anything else, if you let the system just do what it wants to inside of its walls, then that W doesn't change. And the probability of observing any one microstate within that system is assumed, at least by the ergodic hypothesis, all to be the same. Now let's suppose instead of finding the probability of just one microstate, I want to find the probability for a set of microstates, and we'll call that set S. And we'll see cases, that set is a little vague right now, but we'll see cases where we'll define a little better what that set is later. then the set of microstates also has a certain number of microstates in it, right? So I have a big set, I've got a lot of microstates, I've got a little set. The littlest possible set is just one microstate, right? Then there's just one microstate. That's the one that's in the numerator in the previous expression. But if I've got a bigger set with more microstates in it, then I just count how many microstates are in that set. I divide it by the total number of microstates for all possibilities, and that's my probability. So the probability is just the fraction of all microstates in my set S. The fraction of all possible microstates in S is the probability. So what this is saying, and it's an important result, all of this stuff's really important, these are the basics, is that if we want to calculate probability, all we have to be able to do, the only thing we have to be able to do, is count microstates. You can count microstates experimentally, but you can also count microstates theoretically by just thinking about the system and counting how many microstates it would have. Since probabilities are measurable, that means that if we can measure probabilities, that's another way, an indirect way at least, of also counting how many microstates the system have. So we can both measure probability and compute probability, and we're going to do both directly or indirectly as we go along. All right, we saw earlier in the class that the entropy is also, we've seen this expression before, is related to this quantity W, which depends on E and V and N, so that if I can find this W somehow, I can also find the entropy of the system. And the entropy of the system as a function of energy and volume and mole numbers is a fundamental thermodynamic potential. And once you have any fundamental thermodynamic potential, you have everything, you have a way at least of obtaining all the information all the thermodynamic information that's possible to get about a system. So for example, if I have the entropy as a function of E up here, and then I take the derivative of that function with respect to E, I get the temperature. And since that temperature came from my function, which depends on E and V and N, that gives me the temperature also as a function of E and V and N, and that's an equation of state. That's one version or one example of an equation of state. And so right away you can see, before we've even done hardly anything, you can see that if I can count microstates here, then I can get entropy, and if I can get entropy, then I can get temperature, which is an equation of state. And so there's a very close connection, a very simple and close connection between the statistics or the counting or the number of microstates available to the system and all the equations of state, the ideal gas law, the chemical potential equation of state, the heat capacities, all the quantities that we've used earlier are all very closely related to this statistical quantity, which is just the number of states available to the system, the number of microstates available to the system. All right, and so I just say that here again. If we can count the number of microstates W for an isolated system, we can also find all of its thermodynamic properties. That's the promise of statistical mechanics, and we'll see how that promise works out in what's coming next. I'll stop here and we'll pick this next major topic up, the Boltzmann distribution, in the next lecture.